All right, so this is a look at the data representation practice problems. So for a decimal or a base 10 number 51, what is the equivalent binary, octal, and hexadecimal number? So I'm going to start with binary, and there are two different ways we learned how to convert from decimal to binary. One is the greedy algorithm. All right, so that's basically what's the biggest power of 2 that can go into 51. So again, if we're thinking about our powers of 2, we've got like 1, which is 2 to the 0, and then 2, and then 4, and then 8, and then 16, and then 32, and then 64. Okay. Well, we know it can't be 64 because that's larger than 51. So our first number is going to be right here in the 32 slot. All right. Once we've done the 32 slot, we say, all right, 51 minus 32 is 19. So there's only 19 left over. All right. Well, 16 is still less than 19, so we can also have a 1 here. All right. And then when we do this, we say, all right, 19 minus 16 is 3. Well, 8 is bigger than 3, so we can't have a 1 there. 4 is bigger than 3, so we can't have a 1 there. 2 is not bigger than 3, so we can have a 1 there. And then we can have a 1 there. So our final number would be 110011. Right? That's the greedy algorithm. The other algorithm is the division algorithm. So that's where I say, all right, I've got the number 51 here, and I'm going to divide it by 2. I'm going to say, all right, well, that goes in 25 times with a remainder of 1. And then I'm going to divide 25 by 2. And I'm going to say, all right, that goes in 12 times with a remainder of 1. And then I'm going to divide it by 2. And I'm going to say, all right, that goes in 6 times with a remainder of 0. And I'm going to divide by 2. And I'm going to say, all right, that goes in 3 times with a remainder of 0. Then I'm going to divide it by 2 again. And I'm going to say, all right, that goes in once with a remainder of 1. Then I'm going to divide it by 2 again. And I'm going to say, all right, that goes in 0 times with a remainder of 1. And when you get to a 0, that's when you know to stop. And then you read the number top to bottom. All right, so make sure that if you do it this way, you're reading the number in the correct direction. But again, it's giving me the same exact result, 110011. All right, so either way you choose is fine, but this is for when you're going from base 10, which is our regular number system, to binary. All right, so this technique, either one of these techniques work from going to base 10 to binary. Now, to convert to octal and hexadecimal, I am going to use the shortcut. Later on in these sheets, I'll do it the long way, but I'm going to do the shortcut. And the shortcut only works when you're going from binary to octal, or binary to hexadecimal, or hexadecimal to binary, hexadecimal to octal, in either direction. But to go from binary to octal, you just have to recognize that 3 binary digits can convert to 1 octal digit. So you always start on the right-hand side and go left. So my first group of 3, because you can't start at the left-hand side because depending on how many digits there are, it might not work out cleanly. So for my octal, I would have 2 octal digits. So I would say, all right, well, what's this number in binary? Well, that's the 1's place, that's the 2's place, that's the 4's place. So this right here is the number 6. So it's an octal digit 6. This number is the 2's in the 1's place, so that's an octal digit 3. So an octal, 51 looks like this. All right, in binary, it looks like this. And then for hexadecimal, we have to use 4 digits. And this kind of shows you why it's important that you start at the right-hand side. So these 4 digits will be my first hexadecimal digit. these 4 digits, and I can just put zeros in there, will be my second digit. So in this case, they're both just 3. All right. There's a 1 in the 2 spot. There's a 1 in the 1 spot. So as a hexadecimal number, this would just be 33. Okay. So again, you need to be comfortable going from a decimal number to either binary, octal, or hexadecimal. Now, I like doing the shortcut of going to binary first and then getting octal and hexadecimal that way, but I will show you the long way later on in this sheet. All right, the same bit pattern can be interpreted in different ways. For example, the 8-bit pattern 01000001 could represent a binary number, but suppose it represents an ASCII code instead. What letter would it represent? Now, you do not have to have the whole ASCII table memorized, but if I give you a table, you have to be able to use this table and look up what value that would represent. So in this case, we're doing 0, 1, and then a whole bunch of ones, which brings us to this one right here. So what letter would it represent? A. And make sure you are specifying between uppercase and lowercase because they do have different encodings. So you don't want to be lazy and just be like, oh, it's an A. No, it's actually an uppercase A. So I'm just making that very explicit. All right, for the binary number, what is the equivalent decimal number? So again, this is going in the other direction. All right, so it says does not use sign magnitude, so we don't have to worry about positive or negative. So remember that each one of these is something to the 2's place. So this would be 2 to the 0. This would be 2 to the 1st. This one would be 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. All right. So basically the zeros get wiped out because you're doing 1 times 2 to the 7th plus 1 times 2 to the 6th plus 1 times 2 to the 5th. Yes, technically you're doing plus 0 times 2 to the 4th, but that's going to get wiped out because it's 0. And yes, technically you're doing 0 times 2 to the 3rd, but again, that's going to get wiped out because it's 0. Then we have a plus 1 times 2 squared. We have a plus 0 times 2 to the 1st, which will get wiped out. And we have a plus 1 times 2 to the 0. All right, so that's what's happening here. The other way you can do it is you can kind of think about it like, so one, you could figure out what that equals. The other way you can do it is you can kind of do the reverse of what we did up here and say, all right, well, I know 1, 2, 4, 8, 16, 32, 64. 1, 2, 3, 4, 5, 6, 7, 128. Okay. And then if we look at our number, we say, all right, 1, 0, 1, 0, 0, 1, 1, 1. And then you're only adding together the numbers that have the ones. So this one, this one, this one, this one, and this one. All right, so whichever way you do it is fine, but you need to be able to go from binary to decimal. So 4 plus 1 is 5, plus 32 is 37, 97, 101, 229. All right, so again, your call kind of how you want to do that, but that is one way. All right, next, for a hexadecimal, base 16 number, 32A, what is the equivalent decimal number? All right, so this time, instead of doing powers of 2, we're doing powers of 16. So this is 16 to the zeros place. This is 16 to the first place. This is 16 to the second place. So when we're writing this out, this is 3 times 16 squared plus 2 times 16 to the first. And then with hexadecimal, you have to remember that A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And F is as high as it goes. So F would be my last one. So this is A. So it would be plus 10 times 16th to the 0 power. And then after that, it's just kind of going through and working out what that equals. All right, and when you kind of work that all out, you should get 810. All right, this piece right here is going to be 768. This piece right here is going to be 32. And this piece right here is just going to be 10. Okay. All right, for the octal number 723, what is the equivalent decimal number? So again, just making sure that you're comfortable with all of these, but it's the same general process, all right? This is 8th to the 0 power. This is 8th to the first power. This is 8 to the second power. So when we're working out the decimal equivalent, it's 7 times 8 squared plus 2 times 8 to the first plus 3 times 8 to the 0. And then once you've got that, it's just a matter of working out what it equals to. All right, so this is 7 times 64, which would be 448. This is 2 times 8, which would be 16. This would just be 3. So altogether, you would end up with 467. All right, suppose the 3-byte pattern 000111111100000 represents a color triplet. What color does it represent? All right, so it's important that you realize that the first one is red, the middle one is green, and the last one is blue. So this is green all the way on, red and blue all the way off. So this would be green. All right, some common ones that you should be familiar with. Everything off is black, everything on is white, and then you should know that red comes first, green's in the middle, and blue comes last. All right, for the decimal number 537, what is the equivalent octal base 8 number? So again, there's 2 ways to do this. You either turn it to binary, and then you do the 3 binary digits as an octal digit trick, or you convert it straight to octal. Now, if we're going to convert it straight to octal, we use the same division algorithm that we used before, only now instead of dividing by 2, we're dividing by 8. All right? And 8 goes into 537 67 times. All right? And there is a remainder of 1. All right, so it goes in 67 times with a remainder of 1. Then we would divide 67 by 8. All right, now that's going to go in 8 times. 8 times 8 is 64. So then we know the remainder is 3. So this is going in 8 with a remainder of 3. We divide by 8 again. We get 1 with a remainder of 0 because nothing's left over. And then a lot of times kids want to stop here, but you actually have to go 1 more. And we say, all right, it goes in 0 times with a remainder of 1. You don't stop until you get to the 0. And then we read our numbers top down. So 537 in decimal would be 1031 in octal. Right? And that little 8 down there designates that it's octal. I guess I could have done that right here. This is octal. This is hexadecimal. All right. So hexadecimal, same exact thing. I could turn it to binary and then do my 4 binary digits is 1 hexadecimal. Or I can use the division algorithm. And I can say, all right, 355 divided by 16. So 355 divided by 16 goes in 22 times. 22 times 16 is 352, which means the remainder is 3. Then I would divide this by 16 and say, all right, that's only going to go in once, and the remainder is going to be 6. And again, I don't stop. I then say, all right, this is going in 0 times, and the remainder is 1. So my final answer here in hexadecimal is 163 base 16. Now be careful with these remainders. Sometimes you're going to get a remainder of 10. Sometimes you're going to get a remainder of 11, 12, 13, 14, 15. Then you have to remember that a remainder of 10 actually corresponds to an A. A remainder of 11 is a B, a C, a D, and E, E and F all the way up to 15. So just make sure if you get a remainder above 9, you're translating it to the appropriate letter when you actually move it to hexadecimal. All right. And then again, you either do it this way or you convert it to binary, and then you do the 4 binary digits is 1 hexadecimal digit, right? Which is what I showed back here. All right. Either way is fine. It's up to you how you want to do it. All right, moving on to the next sheet. Convert the sign magnitude number 1101001001 from binary to decimal. All right, so sign magnitude is where you have to remember the first digit is no longer part of the conversion. This tells us whether it is positive or negative. All right, a 1 implies that the number is negative. A 0 implies that the number is positive. So in this case, we are looking at a negative number. Then we use the rest of this to actually convert to a number. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different digits there that we can use. But this last digit here is just telling us whether it's negative or positive. So again, you've got to convert the rest of the problem is exactly the same as all the other ones. So I could be like, all right, got my 1 spot, my 2 spot, 4, 8, 16, 32, 64, 128, 256. So I've got 1 here, I've got 0 here, I've got 0 here, I've got 1 here, 0, 0, 1, 0, 1. And then that last one is not part of my number. It's just telling me whether I'm positive or negative. All right, so I know that my answer is going to be negative because I have a 1 in that spot. And then the rest of it's exactly the way I normally do it. So I'm going to take 256. I'm going to add 64 to it, which is going to get me 320. Then I'm going to add 8 to it, which is going to get me 328. And then I'm going to add 1 to it, which is going to get me 329. All right, so you can basically pretend like that last digit isn't there. Do it the way you normally do it, you know, whether it's this way or whether it's doing the 1 times 2 to the 8th, 2 to the 7th, 2 to the 6th, 2 to the 5th, so on and so forth, or whether you do it kind of this bucket way. And then that last one is just telling you whether the answer needs to be positive or negative. Okay. Okay, next is not asking you to actually do a conversion, but it's asking what is the largest sign magnitude decimal value you can represent using 1 byte. So let's start by just showing what that number would be. All right, so largest means that it needs to be positive. So the first digit is going to have to be a 0. Now, 1 byte is 8 bits. So the largest possible number is going to be a 0 followed by 7 ones. Right? Now, what is that actually as a number? All right, well, again, let me make my 8 little buckets here. All right, the first bucket is just your positive negative bucket. And then this is 1, 2, 4, 8, 16, 32, 64. Now, all of these have a 1 in them. This one has a 0, which tells us the number is positive. And then it's just saying, all right, 64 plus 32 is 96. 106, 112, 120, 124, 126, 127. All right, so this would be 127. Now, the other way to do this without actually having to say like, oh, there's 7 digits and this is the number and let me convert that number, is to say to yourself, all right, so I've only got 7 bits to work with here because the 1 bit is the sign bit. So 7 bits would be 2 to the 7th minus 1. And the reason we subtract 1 is that one of those arrangements is being used for the value 0. So 2 to the 7th gives you 128, but when we subtract 1 from that, there's where the 127 is coming from. Now, if we were asked about the smallest number, all right, the smallest number would just be 1, 1, 1, 1, 1, 1, 1, 1, which would be negative 127, because a 1 in that first spot means that we have a negative number. And then if we wanted to know the total number of combinations, so total numbers, we'd have the positive 127 to the negative 127. So altogether, that's 254 options. But then we also have a 0, so that's 255 options. All right, 255 different numbers, which is the same as 2 to the 8th, which would tell me how many combinations there are. But because we have both a negative and a positive 0, that's where the 255 is coming from. All right, so we kind of lose one of our possibilities because of the double 0, right? So again, you can either kind of do it this way where you say, all right, well, this is the positive, so this is the negative, so let me double that and then add 1 for the 0. Or you can say to yourself, all right, I've got 8 bits, so that's this many combinations, but I have to subtract away 1 because we're wasting, because we have a positive and a negative 0. But either one will work. All right, what is the smallest sign magnitude decimal value you can represent using 2 bytes? All right, so 2 bytes would be 16 bits. So that would be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Right. Again, this one is my positive negative bit. So if I'm looking for the smallest value, I've got to be negative. And then remember, negative, like, so the bigger the magnitude, the smaller the value actually is. So it would be all ones. Now, this is where it gets annoying to have to do this, because now all of a sudden I've got like 15 boxes that I have to add together. So this is where it's helpful to say to yourself, all right, well, I've got 16 bits. One of those bits is being spent on the sign. So really, my largest number is going to be 2 to the 15th. And then I have to subtract 1 because one of those combinations is for 0. So I don't get to go all the way up to 2 to the 15th. I go up to 2 to the 15th minus 1, which gives me 32,767. All right, this would be the smallest. And then if I wanted to know the largest, that would start with a 0, and then 1's the rest of the way. All right, so that's the biggest number possible, but the 0 means that it's positive. Sorry, this would be a negative because we were doing the negative there. So that's negative 32767. Positive would be the same exact thing, only it would be positive 32767. So if you wanted to know the total number, you could multiply one of these by 2 and then add 1 because you have to account for 0. So if I'm talking about the total different numbers I can represent, I can either do 32,767 times 2 plus 1, which is 65,534. Or I can say to myself, oh, okay, well, that's 2 to the 16th minus 1 because I have both a positive and negative 0. So I don't get to count those as unique numbers. All right, so in both of these, we're subtracting 1, but we're subtracting 1 for different reasons. Here we're subtracting 1 because we have to represent the value 0. Here we're subtracting 1 because we've actually represented 2 zeros and we have to take away one of those possibilities. So again, either way you do it is fine, as long as you end up at the right spot eventually. And I am sorry, this is not the right spot because I didn't actually add the 1 there. This should be a 5. So as long as you end up at that right spot, you're in good shape. All right, and any way you get to that is fine, as long as you're able to say, oh, with this many bits, I'm going to have this many unique combinations. This is my highest possible value. This is my lowest possible value. And again, when it's small enough, it's easy enough to do it like this and say, oh, let me just actually write it out and convert it. That gets a little more annoying when you start dealing with like 2 bytes or 3 bytes or 4 bytes. Then you are going to want to be familiar with how these exponents sort of connect with everything. All right, number 12 is sort of a trick question. It says, what is the smallest unsigned decimal value you can represent using 1 byte? All right, well, unsigned means we're not worrying about positive or negatives. So the smallest value would just be 0. All right, that would be 0, 0, 0, 0, 0, 0, 0. Right? That would be the smallest possible value. All right, the largest possible value would just be 1, 1, 1, 1, 1, 1, 1. All right, and this time, because we're not wasting a byte on the sign, we would get all the way up to 255. Like if you converted that from binary to decimal, you get 255, which again is 2 to the 8th minus 1, because again, we use one combination to represent 0. And if you're talking about the total number of combinations, there are 256 unique numbers, which is 2 to the 8th. And I don't have to subtract 1 this time because I don't have the positive and negative 0 that I have when I'm doing sign magnitude. So sign magnitude has this little inefficiency where you end up with both a positive and a negative 0. Going back up here, like this would be negative 0. This would be positive 0. So we're actually wasting a combination because these two combinations both mean 0, which is why we're subtracting 1 here. But when we're not worrying about positive and negative, we don't actually have to subtract 1 here. We have 256 numbers, and those numbers go from 0 to 255. All right, so it's just important to pay attention to whether it's talking about signed, where you lose a bit so that you can identify whether a number is positive or negative, or unsigned, where you use every single bit just to convert to the number. All right, last two here. Suppose you have an image of height 10 and width 8 such that each pixel stores an RGB color using 24 bits. You then compress the image using the JPEG format, and in that compressed form, its size is reduced to only 600 bits. What compression ratio is achieved with the JPEG format in this example? Express your answer as a decimal number rounded to the nearest tenth. Okay, so a compression ratio is found by doing the compressed size over the uncompressed size. All right. The problem tells us that the compressed size is 600 bits. The uncompressed size, we have to do a little work on. All right, it tells us that each pixel uses up 24 bits. It tells us the height is 10 by 5. So 10 by 5 means that there's 50 pixels in total times 24 bits per pixel is 1200. So our compression ratio is 600 over 1200, or put another way, just 0.5. All right, so we don't have to round it there. It's already rounded for us. So basically, we cut the size in half. All right. And then 14 says, what are the 3 compression techniques we discussed in this unit? All right. The first one was keyword encoding. All right. That's where common words would get replaced by a symbol. So you might say, oh, whenever we see the word the, we're going to use a $sign. And whenever we see the word and, we're going to use an ampersand. And then whenever we see the word it, we're going to use an exclamation point. And then you would go through the text and replace those words with symbols and save space that way, because instead of using 3 characters, you only are using 1 character. Instead of using 3, you're using 1. Instead of using 2, you're using 1, but keyword encoding. All right. Next was Huffman encoding, which is where more frequently used characters get shorter encodings and less used characters get longer encodings. So you might be able to represent the letter A with just like a 0 and a 1. And then you might represent the letter X with like a 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, or something like that. So it's going to be a much longer encoding for the less frequently used letters. And then the last one that we did was run length encoding, which was useful when you had like long sequences of things. So for example, if you had B, 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 A, C, 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 or something like that. Let's go see one more. All right. Instead of writing out all of these B's, we have a sort of a indicator character. So let's just say we're going to use the asterisk here that says we're about to start an encoding. We say which letter we're encoding. So in this case, B. And then we say how many times it repeats. Now notice it takes 3 characters to do an encoding. So we wouldn't bother to encode A because it would actually take us 3 characters to encode A, and it only takes us 2 characters to just write it out. It turns out the lowest one we would actually do it for is 4 characters, because with 3 characters, you're not saving any space, but you are making the computer encode and decode, which is wasteful. Now the C, there are 6 of, so we would do that again and go star C6. All right. So again, those are basically the 3 main ones that we looked at. You should know each of them and just have a general idea on how each of them works. For Huffman encoding, if I give you a table, you should be able to encode and decode stuff. You had that on your homework. There's examples in the notes, but that's the sort of stuff that you should be able to do. Same with run length encoding. You should be able to encode and decode run length. I can either give it to you like this, and you should be able to give me the original, or I can give it to you like this, and you should be able to create something like this. Okay. So again, I hope this was useful. And as always, if something didn't make sense or you need extra help on something, just let me know. All right, bye.